Today's goal is to understand the derivative conceptually through working on homework type problems. Let's start working on, first of all, numerical problems. Remember that the rule of 4, functions can be described verbally, numerically, graphically, and symbolically. Let's start with a numerical problem to help us understand the derivative, where we've got data about a function. Let's look at number 2. For example, in section 2.3, this problem says, find approximate values for f prime of x for each of the x values given in the table. So you see what x varies by 5 units at a time, 0, then 5, then 10, then 15, then 20. And f of x varies in a decreasing way. You can see these values are going down, 100, then 70, then 55, then 46, then 40. You got a table of values. X is 0, then 5, then 10, then 15, then 20. F of x, the function outputs, you could also call this y, is first 100 when x is 0, so f of 0 is 100, then 70, then 55, then 46, then 40. Again, the goal is to approximate values of f prime of x at each of those x values that you're given. You might make a table for f prime of x. Continue the table down here. This is very limited information, right? This is not like a formula where we can say exactly what the output is if we know the input everywhere. Here we only have discrete data, you might say. What goes here, first of all? F prime of 0. You have to approximate it. You can't calculate a limit. Yes, by definition, it is the limit as h goes to 0 of f of x plus h, or f of 0 plus h, I should say, because x is 0, minus f of 0 divided by h. We can't actually do the limit because we don't have a formula. We don't even have a graph. We couldn't even estimate the slope of a tangent visually. We will have some problems where we do have graphs in this class today, but not right now. So you have to approximate it. 0 plus h is h, so this is approximately f of h minus f of 0 divided by h when h is small. But that just begs a question. What does small mean? You know, how small is small? Is 0.01 small? Well, not compared to 0.00000000001. It's not. Okay, is that other number I just said that I won't try to say again, is that small? Not compared to 10 to the negative million power, it's not. So what is small? Well, okay. Usually, for most functions we encounter that model something reasonable in real life, yeah, 0.01 is probably small enough. Maybe even 0.1. But here we don't even have values close to 0. We got the next values at x equals 5. So that's the best we can do. That's our best measure of small given the limited information that we have. So for this problem, we would have to approximate it as f of 5 minus f of 0 divided by 5. We'd have to take h to be 5, which is not typically considered to be a very small number. But it's the best we can do. That's often the case in real life, is you have limited information. You've got discrete data. A common kind of example is business data, right? You measure your sales over the course of 1 month. You're not measuring your sales every instant of every day unless you're a humongous company like Amazon, okay? So you have to do your best with the data that you have. In this case, f of 5 is 70, f of 0 is 100, h is 5. So this is negative 30 over 5, which simplifies to negative 6. That's your best estimate for f prime of x when x equals 0. What about when x is 5? This gets a little trickier, and there possibly could be more than one answer for this one. Why? F prime of 5 is, yes, the limit as h goes to 0 of f of 5 plus h minus f of 5 divided by h. And yes, this would be approximately f of 5 plus h minus f of 5 divided by h when h is small. But once again, we have very limited information. We know the values of x every 5 units. Seems like we'd have to take h equal to 5 again, right? Or is that the only choice? We sort of implicitly imagine h to be positive. That's the way I've drawn it when we've drawn slopes of secant lines. But h could be negative. We could use h equal to -5 as well. Seems a little weird. Maybe we should try it both ways and see if we get the same answer or two close answers. If h is 5, this is f of 10 minus f of 5 divided by 5. F of 10, look up here, is 55. F of 5, we saw with the previous one, was 70. It's like negative 15 over 5 is -3. But what if we took h to be -5? 5 plus -5 is f of 0. Is 0. And so we'd be plugging that into f. And if h is -5, I guess we'd be dividing by -5. That's kind of weird. And actually, if you compare it with this, the numerator and the denominator are the opposite of what they were before. This is going to be, instead of 70 minus 100, it's 100 minus 70. And instead of dividing by 5, we divide by -5. But we still get the same estimate for the derivative, -6, that we did at x equals 0. So what's the right answer? Technically speaking, with this limited information, we don't really have the right answer. These are all just approximations. Probably the best thing to do here at a value of x that's not at an endpoint, 0 or 20, like 5, is to take the average of these two numbers. That's probably the best thing to do. Doesn't that seem logical as probably giving us the best estimate? So our best estimate, I'll put the word best in quotes, best estimate for f prime of 5 would be the average of -3 and -6. -3 plus -6 divided by 2, -4.5, halfway between them, right? Yeah, this is the average of two negative numbers, but you still add them and divide by 2. And their average is going to be negative. Yes, it is halfway between them. In the absence of other information, this seems like the best option to me. Certainly if your function is reasonable and not oscillating too rapidly, for example, if it's just sort of changing in a gentle way, this seems like probably the best option. I mean, we can go ahead and make a graph here of the data to help it seem more reasonable. X is 0, then 5, then 10, then 15, then 20. Guess the function's up here, starting at 100, going down to 70 when x is 5, going down to 55, not quite as dramatic of a change there when x is 10. Seems like the true underlying function is not only decreasing, but probably concave up. When x is 15, it goes down by 9 more instead of 15 more to 46. Not as big of a drop again. And then only down by 6 for as x goes from 15 to 20. Now, I'm not going to connect these dots, but I could with a smooth curve. And if you had good physical reason to believe it's a smooth curve, connecting these dots, and again, not something oscillating wildly that just happened to go through these 5 points, then yeah, this seems like the most reasonable thing to do. I would say go ahead and do it. Will it match the answer in the back of the book? To tell you the truth, I'm not positive. Maybe the back of the book picks -3 or -6. Maybe it defaults to -3 in this kind of problem. Or the answer in the electronic book. Well, I guess this is an even problem anyway. I will tell the grader that you can average when you've got numerical information like this, when you're not at an endpoint. Let's see if we can do the other ones in our heads here, or my head at least. At x equals 10, I'm just looking at the table now. I should estimate f prime of 10 to be maybe f of 15 minus f of 10 divided by 5. I can do that in my head. 46 minus 55 is -9. Divided by 5 is -1.8. Okay, that would be the forward estimate. What about the backward estimate? It would be the -3. Average, okay, I'll write it out. -1.8 and -3. And you're going to get -2.4 as your best estimate for f prime of 10. At x equals 15, we are going to use the -1.8 from the previous slope. We're really calculating slopes of straight lines here between these points. Secant lines really have the curve. The -1.8 is going to be relevant again. What are we going to average with it? How about -6 over 5? The function goes down by 6 as x increases by 5 there. -6 over 5 is -1.2. This is going to give you -1.5 as your best estimate. And at x equals 20, now we're at the right endpoint. Now we only have effectively one data point we can use. F of x goes down by 6 as x increases by 5, -6/5, -1.2 as our best estimate for the derivative there. Okay. In the absence of other information, in the absence of fancier numerical methods, actually there are fancier numerical methods that give you more accurate results at the endpoints in particular, this is the best that we can do. Okay. Maybe you would be asked to graph the derivative as well. Well, you could graph these points. When x is 0, y is -6, then -4.5, then -2.4. The derivative is an increasing function, but negative in value, heading up towards 0. I guess I started connecting the dots, and I guess I will continue to connect the dots there. And let me go ahead and connect the dots anywhere. I said I wasn't going to, but I guess I will. Let's just pretend it's a nice, smooth, decreasing function that's concave up, because that seems reasonable at least. Really, in reality, if you were trying to apply this in a real-life situation, you want to have, again, physical or business-related reasons to know the function's not oscillating too wildly. You'd want to know that. Okay? And in most situations, it would not be. You get wild oscillations when things oscillate wildly, like a mass in a spring that's oscillating wildly, or maybe a light wave that's oscillating wildly, or maybe an earthquake. Measurement of an earthquake oscillates wildly. Those are examples of things that oscillate wildly in real life. But most physical and business situations don't do quite that extreme, at least over short time intervals, you might say. Let's next do a graphical problem. This looks like an interesting one, number 10 here. And I can actually make this graph bigger. View the image here in a separate window. Oh, isn't this nice? Going to be able to see both easily here. So this is the graph of some function. What do the directions say? The directions say graph the derivative of this function. Okay, if it wasn't clear about what we talked about last week, or the example we just did numerically, the derivative is a function. On the homework you turned in today, you focused on the derivative at a point, at a single value of x, giving you the slope of the tangent line of the original function at that value of x. But we can do that for any value of x. So in reality, the derivative is a function. So what does that mean here? It means I'm trying to estimate the slope of this graph at every value of x. Estimate. It's not going to be perfect. If you actually have a physical copy of the book, I was going to bring a ruler with me. Actually, I was, but I was looking through my desk and I couldn't find one. You could get a ruler out and measure, even draw little line segments for mini tangent lines and measure the slopes. Compute rise over run. Okay, I can't really do that so easily here. Can imagine with me with this cursor here. Say I'm at x equals -4. By the way, the x-axis seems like it's this horizontal line in the middle, and the y-axis is the vertical line in the middle. It would have been nice if they'd made that a little bit darker to see it more clearly. Right there where x is -4, what's the slope there? Oh, it's pretty close to straight there, isn't it? What's the rise over run if I pretend that's a line? Well, the run's 1 unit. X is going from -4 up to -3. The rise looks like y goes from about 0.2 to about 0.5. About 0.3 for the rise and 1 for the run. Although the tangent line is going to increase a little bit more because this is slightly concave down, I think. Maybe 0.3, 0.4 for the slope of the tangent line right there. So in graphing the derivative and maybe even trying to make graph paper here very quickly, so I'm not doing a very careful job. You don't have to do this, but I'm trying to give you the idea. When x is -4, the derivative value is close to -0.2, or excuse me, mistake, +0.2 or +0.3 or so. As x continues to increase, like to -3, you can see, because the graph is slightly concave down, that the slope is a little bit smaller. Still positive. That tangent line that would be there would be still positive in slope, but pretty close to 0. Maybe 0.1 or 0.2, slightly lower, but still positive. Once I get to right about here, x is -2.5. There you can see the graph changes from increasing to decreasing. The tangent line at this point right about there is horizontal. If you zoomed into the curve near that point, closer and closer, it would look more and more horizontal. So at about -2.5, the derivative, the slope of the tangent, is 0 or very close to 0. Then it becomes negative as x continues to increase. Where is it most negative? Looks like maybe right about when x is -1. Maybe slightly lower, -1.2, -1.3, something like that. The slope of the tangent line would be most negative there. And how negative would it be? I could try to draw a little tangent line here and try to estimate its slope. If I pretend let's just do it at x equals -1. If I pretend the tangent line goes like this, see the cursor there? X increases by 1 and y goes down from what? About -0.7 down to about -2.2. I'm imagining following the tangent line here. That's a drop of 1.5 as x increases by 1. A slope of -1.5 divided by 1, -1.5. That's when x is, this is when x is 1. Okay. Down to -1.5 for the derivative, right around there. Oops, no, another mistake right there. Ignore this. This is a mistake. Ignore that. That's a mistake. Looks like the derivative becomes 0 again when x is slightly negative. -0.2 or something. The derivative appears to be 0. So the graph of the derivative is going to go back up to 0 right when you get to x is about -0.2. Then it'll become positive and reach a maximum positive slope right around when x is positive 1. And the slope of that looks like maybe it's close to 2 when x is positive 1. Let's just pretend it is 2. And then it decreases, but stays positive. And once you get to x equals 4, you get a slope maybe of about negative or positive 0.4 or so. Something like that. Connect the dots now. Maybe you want to fill in more data, but connect the dots not in a haphazard way, but carefully with a smooth curve. The original graph smooth. It should seem reasonable that this new graph is smooth. Try to make it as nice looking as you can. Something like that. Question? Why is it going down here? Is that what you're asking? Yeah. Yeah, it's going down here because this graph, while it's still increasing, is concave down. So the slope here, you see how it looks like part of a frown there? The slope is getting smaller and smaller. It's close to 2 here. It's close to positive 0.4 or so here. So it's got to go down in value. Now, one real subtle thing is I did make it look like maybe there's a point where the derivative has a maximum, itself has a maximum slope, negative slope right around there, but that's not necessarily the case. The derivative doesn't necessarily have what's called an inflection point right there. This is a reasonable graph of the derivative. We're not looking for perfection here. We're looking for reasonable. Though we are looking for pretty good, especially where the derivative changes sign from positive to negative there at about negative 2.5. Again, in this graph corresponding to this point right about there. And changing sign from negative to positive right at about negative 0.2, corresponding to this point here. And those are the only two places it changes sign from positive to negative or vice versa. Another question? You're wondering what this is here? I think this negative 4 is referring to x being negative 4 right there. X is negative 3 right here, negative 2 right here, negative 1, 0, 1, 2, 3, 4. It's a little bit strange way to mark the graph, but I think that's what they mean. Some of the graphical problems don't give you grid lines like graph paper. You just have pure graphs, like some of those there, or like this one here. This one's kind of interesting. We've got a graph of some function. We've got 6 different values of x that are marked. What are we being asked? We're asked to identify where is the function greatest and least, where's the derivative greatest and least. And I'm also going to do something else with this. I'm going to turn it around and pretend it's the graph of the derivative and ask, what about the original function, if that's the case? That's not what's being asked here, but there are future problems where that kind of thing is asked. Well, let's do what's asked first. That's our function f of x. Where is f of x greatest and least? Just where this graph is highest and lowest. That's pretty easy. You don't have to know calculus to know about that. At these 6 marked points, not overall, but at the 6 marked points, the function is highest at x3, right? And lowest looks like x4. So f for this problem, I don't know which problem number this was, looks like it's number 37, is greatest at x3. Nothing to do with calculus there. I'm just looking at this plain old graph and not even thinking about slopes at all. Just where is it highest and least of these 6 marked points? And f is least at x4. In fact, I might ask this on the test. Order the function values from least to greatest. If you're going to do that with less than signs, you'd say f of x4 is the smallest. The next smallest looks at like it's at x1. That's less than f of x1. It's also negative at x5, but closer to 0. So this is less than f of x5. I might want to add, where is the number 0 in all this? 0 would be next. 0 is not an output at one of these marked points, but it is indicating all these numbers are negative. Then it looks like f of x2 is next, then f of x6, then finally f of x3. I have asked this kind of a question on an exam in the past. But again, there's no calculus there. Let's do the same thing with the derivative. Based on this graph being the graph of f itself, where can you say the derivative is greatest and least? The derivative is greatest where the slope is steepest in the positive direction of the slope. It's got to be a positive slope. Looks like it's probably x5, right? Steepest there. So you'd say f prime is greatest at x5. It's steep there with a positive slope. Where is the steepest negative slope, if there are any with negative slopes? Looks like there's only one spot here with a clear negative slope, and that's at x3. F prime is least at x3, right? x6, it looks like the slope is close to 0. x4, slightly positive. And so I would also add, if you were asked to identify the derivative values in order from least to greatest and identify where 0 fits in there, I would write f prime of x3 is less than, again, f prime of x6. The slope of the tangent looks close to 0 there. Yeah, I would say that's so close, I'm going to call it effectively 0. This is less than 0, which at least is approximately f prime of x6. And all the other slopes are at least slightly positive. At x4, it's ever so slightly positive in slope. So I'd write this as less than f prime of x4. How many we have left? x1, x2, and x5 are left, right? F prime of x5 is the biggest. It looks like f prime of x2 is next. Then f prime of x1. Then finally, the biggest is going to be f prime of x6, or 3, sorry. 5, sorry. It's a 5. Yes, f prime of x2 is smaller than f prime of x1, even though the function's higher at x2. The slope of the tangent is smaller than the slope of the tangent here at x1, because the graph is concave down. The slopes are getting smaller. Concave down looks like part of a frown. It's concave down all the way until about there. When it becomes concave up, that looks like part of a smile or a full smile, and then it becomes concave down again. This is going to be one of our main topics on Wednesday. Concave down means like it looks like a frown or part of a frown. The slopes are getting smaller. Concave up looks like a smile or part of a smile. The slopes are getting bigger. Yeah, what would happen if we turned the problem around? As will happen in later sections. Maybe not until chapters 4 or 5. What if this were the graph of the derivative instead of the function f? What if this were the graph of f prime? As far as saying where f prime is least or greatest, it would be what we found for f, for the original problem, because this would be the graph of f prime. I'm imagining changing the problem here, saying that's the graph of f prime. If I wanted to find where f prime then is greatest and least, it would be the same as the answer I got for f, for the original problem, because that is the graph of f prime then. But what about f? I'm not trying to estimate slopes of my graph. I'm instead trying to imagine a function whose slopes are given by this graph. Whoa, that sounds tricky. But it is doable. Let me try to sketch a function whose slopes are given by the original graph. So for example, when I'm over at x1, the value of this function is negative, so I need to draw a function whose slope is negative. Where should I start it? It doesn't matter actually where I start it. Just draw it so its slopes are negative. Maybe I'll draw it purposely up here and not closer to the axis here. And this might be x1 right there. I'm not lining it up perfectly. The slope is going to reach 0 between x1 and x2 because that's where this function is 0. And then the slope is going to become positive. If x2 is right here, say, I've got to draw something in such a way that the slope is 0 between them and then becomes positive. The slope is going to stay positive because this function is positive all the way until I get to x is 0. Maybe something about like that. Maybe I should have drawn the graph lower. Then because this graph goes negative, now the slope's going to go negative and only get back to 0 when I get just past x5. If x5 is right here, say, the graph is going to be negative in slope until I just get past x5. So something about like that. And then it'll become positive again. So there's a real rough approximation for a function whose derivative is the given function. It's the opposite kind of problem. Can I tell where it's greatest and least for these values of x, x1, x2, x3, x4, and x5, and x6? It's hard to know for sure. I think I won't try to answer the question. I'll save that question for later. But I just want you to realize at the moment that you can go the other way. That's called integration or anti-differentiation. Instead of finding a derivative, we're finding an antiderivative. Going the opposite direction. It's a really important thing in calculus. Maybe you even thought about it already in your physics class. Problem 32 says, in each case, graph a smooth curve whose slope, read derivative, meets the given condition. Part A, everywhere positive and increasing gradually. Part B, everywhere positive and decreasing gradually. C is everywhere negative and increasing gradually. And D is everywhere negative and decreasing gradually. Yeah. We want the slope to satisfy these properties. For problem 32 now. We want the slope in part A to be everywhere positive and increasing in slope gradually. That's positive, so you got to have a graph going up as you move from left to right. If I want the slope to increase, what do I want? Straight, concave up, concave down? I want the slope itself to increase gradually. Concave up. Does it matter where I put it? No, not really. Something about like that has a slope that's increasing. That's positive, first of all. You're going up. And the slope itself is also increasing gradually. Positive slope and decreasing gradually for the slope means it's going up, but it's concave down. Focus on what the directions say. That's about the slope being positive and decreasing gradually. C, everywhere negative and increasing gradually. This is trickier. So I want to draw a graph whose slope is always negative, but that slope is increasing, which means it's actually getting closer to 0, because on a number line, if you got a negative number that's increasing, that's moving, it means it's moving to the right. Even if it stays negative, it increases as it moves towards 0. So it needs to be concave up as it decreases. I happen to draw it through the origin. It doesn't have to go through the origin. And then D, negative and decreasing gradually. Negative slope, so it goes down. And it's got to be concave down. That slope is decreasing. It's getting more and more negative. If you imagine the value of the derivative on a number line, it's moving to the left on a number line. Once again, I made it go through the origin. It doesn't have to. 33 says, draw a possible graph of a function given the following information about its derivative. F prime of x is positive when x is less than -1, negative when x is greater than -1, and 0 at -1. So here, when we make our graph, we would have to indicate where x is -1 is. Say right there. Just says draw a possible graph. There's actually infinitely many answers. We want the derivative to be negative when x is greater than -1. Part of the confusion here for many people is just dealing with greater than and less than signs. When x is greater than -1, that thing means greater than, to the right of on a number line. F prime of x is negative there. It's less than 0. So whatever graph I draw, I've got to make the slope negative when x is bigger than -1. And positive when x is less than -1. And 0 when x equals -1. So here is a possible graph. I made it look like a parabola. Does it have to be a parabola? No. But that's a simple graph that satisfies those conditions. What you're really trying to understand here is the concepts of calculus as well as the notation and the verbal descriptions, as we saw in the other problem. Sometimes the problems are phrased in terms of applications. 54 is kind of an interesting problem. In problem 54, reading here, it says a child inflates a balloon, admires it for a while, then lets the air out at a constant rate. So imagine it's you blowing up that balloon, looking at it, admiring it for a while, then letting it go. Probably not letting it go fly off into the air, because probably it's not coming out at a constant rate then. So you probably have to hold it and let the air come out. V of t gives the volume of the balloon at time t, and the graph shows its derivative. So this graph that you see here is not the graph of the volume. It's the graph of the derivative of the volume. We want to know, when does the child begin to inflate the balloon? When does the child finish inflating? And when do they begin to let the air out? And also draw an alternative graph for V prime in a different situation, if the child alternated between pinching and releasing the open air of the balloon instead of letting the air out at a constant rate. Let's focus on the first three parts here. Begin to inflate, finish inflating, and begin to let the air out. This is the volume rate of change as a function of time. It might not be a bad idea to draw a graph of the volume itself. We're really doing the exact same kind of problem I hinted at with the other problem as something else you should be able to do 5-10 minutes ago. This is not V of t, it's V prime. What does V look like? You're not actually asked to draw a V, but I don't think it's a bad idea to try to think about this. From time 0 to time 3, V prime is 0. The rate of change of the volume is 0. The volume's got to be constant. Now, is there air inside the balloon before the child blows it up? Yeah, I guess you could say there is. There's just sort of, there's still air molecules going inside the balloon. They're not inflating it. I guess effectively you could say the volume is some small amount for that amount of time. Then at time 3, V prime becomes positive. V must start increasing. That's got to be where the child starts inflating the balloon. It's a little interesting here. V prime increases in a linear way as t goes from 3 to about 3 point, I don't know, 8 or something, close to 4. And that stays constant for a while. The fact that it's increasing in a linear way here means the graph of the volume actually is going to look like part of a parabola at first. And then when this is constant at 1, the slope's got to stay constant at 1. So I don't know if I drew this very well, but I'm trying to make it slightly curved there. And then it's going to stay constant in slope until you get to just before time 9. Maybe you might say time 8 or so, when the slope goes back down towards 0 and becomes 0 again at time 9. So as far as, again, when the child starts to blow the balloon up, it's at time 3. It expands, the volume increases. At time 9, I guess that's where it's maximized in volume. The child has pinched the balloon shut at time 9. And then you can see once we get to time about 14 or so, the derivative becomes negative. So now the slope of the volume function becomes negative. Time 14 or so, that would be when the balloon starts, the child is letting the air out. Notice V prime of, for example, 15 is -2. That's the maximum negative the derivative can be, technically the least value on a number line. And positively, the derivative is maximized at a value of 1. The fact that this is lower, further away from the t-axis than this part is, means the air is being let out faster than it was blown in. So this curve has a steeper slope here than it did over here. And once we get to time 17 or so, that's where we're back to a slope of 0 and being effectively no more blown air into the balloon. Does it come down to as low as it was before? You might say in reality it should. I didn't really draw it that way, but it should. You're also asked to draw a graph of V prime, again, if the child alternates between pinching and releasing after the balloon's blown up, I guess. So you'd start the graph of V prime in the same way. 0, then positive, constant for a while, then coming back down. After admiring it, starting to let the air out, probably the graph's got to look something like this, because the child is alternating between pinching the balloon and letting the air out. When the air is pinched, when it's pinched, no air is coming out. So that would be V prime of t in part D. And you could try to draw a V as well. The downward part would go like this. It would go down and then stay constant, then go down, then stay constant, then go down, then stay constant. Problem 3 from section 2.4 says the time for a chemical reaction, imagine being in chemistry class and trying to get a reaction going, T in minutes, is a function of the amount of catalyst present, A in milliliters. So if you know about chemistry, when you're mixing different chemicals to try to get some sort of reaction, a catalyst is something extra you pour in to make the reaction go faster. Happens all the time in your body, in your cells. There are catalysts in your cells that cause various cell functions, reactions going on in the cells to happen faster than they would otherwise. That's a good thing. Okay. T is a function of A. Before we try to answer these questions, it doesn't ask for a graph, but let's imagine the graph. What might the graph of the time of reaction as a function of the amount of catalyst present look like? I hope it's intuitive that the more catalyst you have, the bigger A is, the faster the reaction will be. Since t is a time of reaction, that means t will be smaller. When t is smaller, that corresponds to a faster reaction. So as a increases, t should decrease. This should be a decreasing function. Is it concave up or concave down or straight? If I had to guess, I'd guess concave up. And the main reason I'd guess concave up is that t can't go below 0. Right? You can't have a reaction that happens in negative time, or even 0 time for that matter. But maybe with a ton of catalyst, maybe the reaction happens, within a millisecond or something. So because of that, it makes more sense for me to think that the graph is probably concave up, though I have no guarantee of that. Maybe it could be something more complicated. It could be concave down at first and then concave up. That would be a more complicated behavior, but it's possible it could happen that way. That's possible. I'm just going to go ahead and pretend it's concave up. Not asked for in the problem, but not a bad idea to do. Part A is not about calculus. It's about interpreting function meaning. If f of 5 is 18, what are the units of 5? What are the units of 18? And what does that tell us about the reaction? Well, 5 is an input. It's the value of A. It's the amount of catalyst in milliliters. T, the 18 is the output. It's the time of the reaction in minutes, 18 minutes, a very slow reaction. That's what it tells you. I just verbally said it. Should I say it again? I'll just say what the equation itself is saying. This is saying that when there's 5 milliliters of catalyst present, the reaction takes about 18 minutes to complete, whatever your definition of completed reaction is. Now, you can get nitpicky in chemistry because there's always reaction going back and forth, but effectively it's at equilibrium, you might say. B is harder. It involves calculus. If f prime of 5 is -3, what are the units for the 5? What are the units for the -3? And what does the statement tell us? This is kind of tricky. So again, we're assuming f of 5 is 18. Let's pretend 5 is right there on the a-axis and 18 is right there on the t-axis. Did I say 15? 18. That's how to interpret part A. Part B says f prime of 5 is -3. The tangent line here has a slope of -3. The slope of the tangent at A equals 5 is -3. That's what it means graphically, but what does it mean in terms of real life, the real life reaction? I'm going to show you Leibniz notation again. I showed this to you last week. T again is a function of A. The Leibniz notation for the derivative writes the derivative as if it were a fraction. D something, D something. What goes in the top next to the D in the top? It's the dependent variable, in this case, capital T. What goes next to the bottom D? It's the independent variable, in this case, lowercase a. dt dA is how you say this when you see it. If you want to just say it quick. If you want to say it more accurately but slowly, you say this is the derivative of t with respect to a. It is a function. We could say it's the same as f prime of a. But for the sake of doing the problem, it's best to plug in a value of a equals 5 in particular. With this notation, with the Leibniz notation, you do it in kind of a funny way. You draw a vertical line after it, and you put the independent variable value down there. That's alternative notation for f prime of 5. dt dA evaluated at a equals 5. You think of this vertical line as meaning evaluated at. So this says dt dA, the derivative of t with respect to a, evaluated at a equals 5, also written f prime of 5, equals -3. Using the Leibniz notation here is really helpful for the following reason. It helps you to remind you what the units for the derivative are. If you pretend this is a fraction, it's the units for the corresponding fractions, which would be units of t per unit of a. The d doesn't affect the units. Units of t are minutes. Units of a are milliliters of catalyst. The units for this would be minutes per milliliter. Well, of catalyst, if you want to emphasize that's of catalyst. -3 minutes per milliliter of catalyst. What does that mean? Well, yes, it does mean the slope of the tangent line is there's -3, but in terms of the real life application, it's telling you that if you increased your amount of catalyst from 5 to 6, say, the time of your reaction would go down by about 3 minutes. More precisely, when A is 5 milliliters, the rate of change, and I would suggest writing this out here as I do it here, of time of reaction, capital T, with respect to, which I'm fine with you abbreviating with respect to as WRT, with respect to amount of catalyst, A is -3 minutes per milliliter. But you really shouldn't stop there. You should really say, so, for example, if A increases by 1 milliliter in this case, from 5 milliliters to 6 milliliters, we should expect the time of reaction to go down by about 3 minutes. The time t to go down by about 3 minutes. Down because the derivative was negative in value. Let's elaborate on that. So we should elaborate what this means as well. So f of 6 should be approximately f of 5. It's going down by 3, so that's the same as plus -3. Same as -3. To be even a little bit more picky, I should say this is -3 times 1. Of course, that does equal -3, but I'm trying to emphasize 1 is the change in A. This is 18 minus 3 is 15 minutes. What I'm using there is the fact that the change in T, delta T, is approximately the rate of change of T with respect to A times the change in A, delta A. That's what this thing represents. dt dA, the derivative of T with respect to A is the -3. Delta A, that's the change in A, is 1. That's because A is increasing from 5 to 6. The total change is the rate of change times the change in A. Total change in the dependent variable is the rate of change times the change in the independent variable. This is very much analogous to distance equals rate times time, except the application is different. It's also an approximation because we're using the tangent line, a straight line, to approximate the curve. If the curve is truly concave up, like I'm guessing it is, the true answer is going to be bigger than 15 in the end. That green graph is higher than the red graph because the green graph is concave up. This will be a bit too small. In reality, it's probably more like 15.5 minutes. All right, have a good day.